All right. So today we have a really nice class. We're gonna do two great things. The first thing that we're gonna do is a spring. So not a regular spring. This spring, we're gonna hit it, and then the spring is gonna do like this, boom, boom, boom. All right. So it's a dynamic analysis. That's the first like new thing that we have in here. Uh, some of you are interested on doing dynamic analysis. Here's a brief intro. This is a completely different beast. All right. This definitely multiplies the phrase that I used to say: if you enter garbage, then you're gonna get more garbage. This in dynamic analysis is even worse. All right. So here's a nice introduction. We're gonna see some element deletion. So what's that? In real life, when you hit something really hard, what happens? Then you start having debris everywhere, right? Like when you see a F1 car crashing, the debris goes everywhere. So today, we're gonna be able to model that. When in the second example that we're gonna have, which we're gonna have a projectile impacting a plate, right? So like a ballistics kind of analysis. I'm gonna record this. Also in my YouTube channel, I have another example where I go more into detail in what are the material properties, why are they like that, and a little bit more into those type of things. Wednesday, we don't have class. All right? I expect everyone to go to the tech symposium on Friday. Remember, who do you have to sign with? Kayla. If you don't sign with Kayla, you didn't go there. Like for me, right? Because she's gonna send me the people that went, 1 or 0. If you didn't go, you didn't go, and if you went there, you just get the extra credit that we discussed. So for the project update, let's skip this Wednesday's update, but then the following Wednesday, which is the one before we go to Thanksgiving, I expect a little bit more, right? So not only what we discussed, but just go that extra step. What is the extra step? Work on your mesh refinement. Those of you who are doing beams, don't refine. So you already saw that. Those of you who are doing 3D, it's really important to focus only in the important areas. Why? That's the reason I brought my laptop. These simulations, if I were to run it in this computer, it will take 1 or 2 hours. It's gonna take like 1 minute on this computer. All right. So be cautious about that too, right? Try to reduce the computational time as much as you can doing those smart modeling techniques. What else? Work on your graphics, right? For the final report, it's a serious final report. Like these weekly updates, it's fine if you just show me a screenshot or something like that. But if we are gonna submit a final report, hey, I saw that here the stress concentration is really high. Then how to reduce that? I increase the thickness of the tube, and then it's not near yielding, but it's below yielding. So those type of things. So start working also on the final report. Why? Because this Wednesday we don't have updates, right? Next Wednesday, Thanksgiving, and then it's like 1 or 2 weeks, and then we're done, right? So this modeling that I'm gonna do, I literally learned it like 1 year ago. So it's advanced stuff, and we're gonna have some fun today with it. So I hope you guys enjoy it. Okay.
So there's no update this Wednesday?
No, next Wednesday, but not only what I said, but do that extra step, right? All right. So the spring, all right? We are gonna model this spring. I don't care about the dimensions too much, right? I just care about the physics and what we are going to do. Advice, don't try to follow me. right? I'm gonna go a little bit quick today because I want to show 2 examples. The material is gonna be aluminum, all right? So our old friend aluminum, we're gonna do something that is called mass scaling. I'm gonna discuss that in a second. It's not good. Mass scaling is not good, but today we need it. So what's easier to move? Something that weighs 1 pound or something that weighs 200 pounds? Right. But however, if you have something really light and you add a pulse, what's most likely gonna happen? Find the equilibrium in something light is really difficult. So what do you usually do? You do mass scaling, right? So you increase the mass of the system, so whatever pulls you up to the system, then the system's like, I didn't feel anything. This is how I'm gonna behave if you give me this pulse, right? So it's a good modeling technique if you want to get a sense of how things behave, but it is not really accurate, right? So today we're gonna use it. We are gonna simulate 1 second. So we are gonna add a really quick pulse, and then we're gonna see how that spring is gonna bounce back, right? And here are the properties. Because now we have mass, right? We're solving the an motion equation. We have to add density in here. So what now we're gonna be solving is a system that has displacements. What is the derivative of the displacements? Speed, right? If you derive displacement with respect to time, it's speed. And what's the second derivative of the displacements? Acceleration. So now we're going to solve the continuity equation that has acceleration, velocity, and displacements. All right? Quick intro to finite element like 3, okay? But I just care about the modeling, and that if some of you are planning to do some dynamic analysis, this is a little bit of an intro, all right? So let's open Abaqus. And I'm gonna work on this working directory that I have in here, all right? So I'm gonna file, set my work directory, all right? And then I'm gonna rename this model, and then I'm gonna call it spring. All right, let's create the spring. So I'm gonna model the plates and the spring in betweens. All right, so for that, I'm gonna use a 3D, right? So let's call this spring as well. It's gonna be deformable, it's gonna be solid, and I'm gonna use a revolution technique, all right? And the size is 20. So the first thing that I'm going to do is to create a rectangle here, and it's gonna be 5 in X and 1 in Y. So it's just that plate that is gonna be on top. That plate, and it's something super important that I just teach these guys previous week, these plates, we are gonna make them rigid. We don't want those plates to deform. We only want the deformation on the spring, right? So that's gonna be my first rectangle, and the second rectangle is gonna start in 0, -10, and it's 5 in X and -11 in Y. So I just created this rectangle, all right? Nothing too complicated. And then I'm gonna revolve this 360 degrees. So I have my upper and my lower plates. All right. Now I want to create a spring. How do I create a spring? Helix. So that's how we call it in SolidWorks. Here, it's just a revolution. And we are going to add something that Abaqus calls pitch. So it's after you do round 1 revolution, where do I end? Do I end in the same place? That's a pitch of 0. But if I want to finish 1.5 millimeters above, that's a pitch of 1.5. And that's how we can create this spring. That's going to make more sense in 1 second. For the spring, which plane do I have to draw? In which plane do I have to draw the cross section of the spring? So I need to draw in a plane, like we do in SolidWorks. XY plane, YZ or XY, either one. Yeah. So I'm gonna go here, and I'm gonna create a plane that is offset from my original planes. So I'm gonna choose XY, and the offset is gonna be 0. So now I have that plane, right? That is cutting my, or is cutting those plates in half. And I'm gonna go here, I'm gonna hold it, and then I'm gonna go to create solid revolve. All right. Where do I draw? I'm gonna draw here. And give me an axis, sorry, an edge that is gonna appear vertical and on the right. I can choose just this one. That step doesn't matter, right? It's just so you can visualize things better. So I don't care a lot about the dimensions. I'm just gonna go here, and I'm gonna draw a circle. That's gonna be the cross section of my spring. Done. All right. So let's do some iterative things in here. Let's revolve it 360. Nothing happened, right? Because it's inside the plate. So how do we modify that? We go here in the solid revolve, and then I'm gonna say, hey, let's edit this. And let's add a degree of 1000. Okay. Let me see. I think, let me try it again. I'm gonna revolve again. So I'm gonna create here on this axis in here. This is gonna be my vertical and on the right. And I'm gonna just simply draw a circle in here. Done. Okay, I have to do it from the beginning, sorry. So I'm gonna add translation and pitch, all right? So let's say that I want to revolve this 1,000 degrees. And my pitch is gonna be 1.5. All right? What happened? Wrong side. All right? So I'm gonna edit, and then I'm gonna say flip pitch direction. So how does it look? Better, right? How much do I have to revolve? We can compute it, right? So we know how much space we have between the two plates, and then we know how much is the pitch, but we don't have time for that. So I'm just gonna go to 2500, and let's see how far it got me. Nice. Not quite there. I want this to be completely inside the plate. So let's say 2600. All right. And there we go. We have our plates and our spring. Questions so far? All right. There we go. All right. Now, I'm going to create two partitions. This plate here on top is going to be like its own partition. Then we're going to have the spring, and then I'm going to have the bottom plate as another partition. All right. How do we do that? Quickly. So whenever you draw, you have circles and you want to cut across that circle, you go here to create partition. And I'm going to say, hey, I want to cut using a plane. And my plane, I'm going to give you 3 points that are on that plane. So first point, second point, this one in here. And then the third point, it could be, for example, this one. Right? So 3 points define a plane. So I'm just defining my cutting plane. If I do that, then look at that. That's its own part now. And then these two are still connected. So I need to do the partition again for that bottom part. All right? So how do we do it? Again, partition. I'm gonna partition this cell that Abaqus calls cells with 3 points. And which one are my 3 points? This one. Let's search for another point. This one in here, and let's search for this one, right? 3 points that are in the same plane. So this point in here, it's really difficult to see, but there's a point in here, that one. All right, create partition. All right. Now I have 3 different, let's call them parts. I have my upper plate, I have my spring, and then I have my lower plate. Everything making sense? All right, let's create some sets, right? Sets make everything easier. I'm really organized, so I like to name everything. So then after, like whenever I'm creating boundary conditions or loads, I don't have to select anything, I just select names. So my first set is gonna be called upper plate, and it is this. So I'm just gonna select that. That's gonna be my upper plate. I'm gonna create another set. I'm gonna call it bottom plate. And that's my bottom plate. You could get the same result by adding 3 different pieces and then creating an assembly. And then saying, hey, this top part of the spring is welded to the top plate, and this bottom part of the spring is bottom to the bottom plate. I think this is way easier. Okay. So that's not the modeling, all right? That's the complicated part of this problem. The analysis is actually quite easy once you find the right parameters, right? But I already did that. So materials, aluminum. Here in general, it's where we add the density. So what's the density of aluminum? 2.8 e to the 9. So I have here the density, 2.7, 2.8, it doesn't matter, e to the negative 9 tons or millimeters cubed. This is the primary source of error in dynamic analysis. If you don't have everything the right things in the right unit system, it's like 90% of the times. Whenever I have an error, it's something related to material properties. So, and then our old friend, elastic. So this one is going to be elastic, 68 gigapascals, and Poisson's ratio of 0.3. Right, I have my material. So I'm just quickly going to create a section. Homogeneous, the same section that we have been creating so far. And I'm going to assign the section to everything. Everything, all right? And we have our beautiful green color. That means that everything is fine, at least in this menu. All right. Let's bring everything into the assembly. So I'm just going to quickly bring this into the assembly. All right. And now I'm going to create 2 reference points. Anyone remembers reference points? Whenever we were doing multi-point constraints. So instead of adding boundary conditions to a set, you can say, hey, all of this set is related to this point. So whatever you do to this point, I'm going to do it to the set. And that's a cleaner way to do things, all right? So I'm going to go here to tools, and I'm going to create a reference point. So my first reference point is going to be here on the top, all right, or P1. And I'm going to create a second one here in the bottom, all right, RP1 and RP2. I'm going to name them correctly, right? I like to be organized. So I'm going to call this bottom plate ref point. This one, right? That's my reference point, which is related to the bottom plate. And I have a top plate ref point, and it is this one. All right. So now they are not RP1 and RP2 anymore. They are top plate reference point and bottom plate reference point. All right. let's do the weirdest thing that we are gonna do in this analysis, which is saying that these plates are gonna be rigid, right? Those plates are not gonna deform. So there's two ways of doing this, and both ways work. One is the bad way, because it's not completely accurate, and it creates source of inaccuracies, and it's creating a material and assigning it to these plates with a really high elastic modulus and density. That way, those plates are not going to deform. Or there's the easy way, and actually saves a lot of computational time, and the correct way, and it's to say, hey, this plate is rigid, and from now on, you only talk to the reference point. You don't talk to the plate. The plate doesn't exist in the simulation anymore. It only exists if you talk to the reference point. So I'm going to go here to constraints, and I'm going to create a rigid body constraint. The name is self-explanatory. That body is going to be rigid. So I'm going to go here, and I'm going to call it top plate constraint. And here in the body, I'm gonna step over body, and then I'm gonna go here to the arrow. That's gonna allow me to select the body that is now gonna be rigid. Do I have to select it here, or we already have a set? We have a set for it, right? So we are gonna select top plate. So I'm gonna go here to spring upper plate. How do I know that it is that one? Hey, highlight the selections in the viewport. So it actually makes sense. It's that one, right? Okay, continue. And then that body is going to be referenced to what? My reference point. And we also have a set for that one. And it's the top plate reference point, which is now highlighted here, right? Continue. And that's my first constraint. So, okay, constraint. Now we see our old friends, right? You remember those circles whenever we were doing multi-point constraints. So now what this is saying is that whatever you do to this reference point, you do it to the plates. So if you add a velocity, all those nodes inside the plate are gonna have a velocity. If you add a rotation, all those plates inside that plate, all those nodes inside the plate are gonna rotate, but they are not gonna deform, right? Because it's a rigid body constraint. Second constraint, same thing, but for the bottom plate. So bottom plate, constraint. So here I go to body, I select my bottom plate. So we already had that one in here. So this one, and I'm gonna reference that to my reference point number 2, which is this one. And that's it. Those are my constraints. What I'm doing is fixing or making those plates non-deformable. Now, let's go to the fun part. Steps. I'm gonna create a step. It's gonna be dynamic explicit, all right? So there's two ways to do dynamic analysis in Abaqus, explicit and implicit. Usually the rule of thumb is that if you have something that doesn't last for more than 1-2 minutes, let's do explicit. So explicit is for like car impact, crashes, ballistic impact, this spring that is just bouncing on a really high speed. So those type of analysis. If you're doing something like, anyone knows what creep is?
I've heard of the materials.
Yeah, when the materials deform, like you apply a load, and then it deforms like super slow, right? Like viscous behavior. How much time do you need to model that? Like hours. Like it's a process that lasts hours. And in that way, it's easier to do it using implicit analysis, right? But for our things that are gonna last less than a second, let's use explicit, all right? So explicit. the time period here, how much time do we want to simulate? 1 second. And we are gonna add mass scaling, right? Don't pay attention to this part a lot, but basically, whenever we're doing the dynamic analysis, Abaqus breaks the simulation into small increments. And for this problem, the stable time increment is 1 to the negative 10. How many increments do we have to do from 1 to the negative 10 to 1 second? 10 to the 10.
Trillion.
And that's a lot of computational power. Like, I will kill this computer. So we are going to do something that is called mass scaling. So I'm just going to create it, and then I'm going to say, hey, my target time increment is 1 to the negative 5. That's more reasonable. This computer can do it. I don't care what you have to do in order to get to this time increment. So what Abaqus is going to do is that it's going to add mass to the system. It's going to add mass, add mass, add mass until the stable time increment is this one. All right? A lot of theory here, but it's just a way to make the simulation go faster. So if you were to ask me, hey, do you trust the results that you're getting? 0%. But I just wanted to show you quickly, right, how to get this model working. All right. There's a certain amount of mass scaling that is allowed, right? I use it in my daily basis. I use mass scaling. Otherwise, my model will take 6 months to run. Okay, with 72 CPUs and a really complex computer. So we use those. So I'm talking about like real life usage in here. All right, so I'm gonna use that mass scaling. All right. Boundary conditions. All right, so my bottom plate is gonna be completely fixed. So I'm gonna say my bottom plate. So do I select the bottom plate or the reference point? The reference point, yes. So my reference point for the bottom plate is gonna be completely fixed. All right. So you see here that we restricted displacements and rotations for that node. What movement is allowed for this top plate? Only vertical, right? So I'm gonna do that. And I'm gonna say, hey, for my reference point of the top plate, allow everything, restrict everything but Y. That plate is allowed to compress my spring. Okay. And now I'm gonna add something that is called Predefine Fields. And I'm gonna say, right at the beginning of my analysis, that top plate was moving at a speed of 150 millimeters per second, right? So I'm adding a pulse. And that energy is gonna be dissipated throughout time. So I'm gonna go here to Predefine Fields. My initial predefined field is gonna be a velocity. Where do I apply the velocity? Top plate reference point. 0 in X. My velocity in Y, let's say that is 100 millimeters per second. So negative 100, right? Because I want to compress it. I could also pull it. It's gonna work either way. And my speed in 3 is 0, right? I only have speed along the Y-axis. What are we missing?
Mesh.
Yeah, mesh. So let's go here to mesh. Important, super important that we go here to S4R. And then we say that is an explicit analysis. If not, you're gonna get an error. So we have elements for the standard, like quasi-static analysis, and we also have elements for explicit analysis. So we have to make sure that in S4R, we have explicit elements. All right?
Sir, I think you mentioned this before, but for the order, what is the difference between the linear and
So for plasticity, this is like deep theory. Like for plasticity, tetrahedrals with a reduced integration, they work better. Why? Usage and error. If you're doing contact works better with quadrilateral second order elements. If you're doing fracture, it has to be hexahedral elements. So it depends on the usage. For this, I'm gonna call them bomb-proof simulations that we are doing. Let's use TET. Tetrahedral meshes anything. It's surprisingly good, and it works. All right. So tetrahedral. So pink, we like that pink color, and the element size, let's do 0.4. Okay. And let's mesh this. Okay, didn't mesh. So let's try again. Let's do 0.5. And let's mesh this. No, wait. All right. So it doesn't want to mesh as it is. So who has experienced that issue? All right, so let's figure it out. All right, so one way to help Abaqus to mesh is to create partitions. All right, so I'm gonna partition these plates in half. So how do I do that? I'm gonna go here, select the cells to partition. I'm gonna partition what? Okay, this partition. And I'm gonna select normal to edge. So I'm gonna, in this edge, I'm gonna extend this point. And now I created that partition. You only get this by creating partitions. It's hard to me to explain every single partition tool, right? You could get to this same thing doing this. Like, let's partition this one, and let's create, and let's partition that with 3 points. So the 3 points of the plane is this one, and then this one, right? I have a plane that is defined by those 3 points. If I create a partition like that, so infinite amount of different ways to partition something. Now let's see if this meshes. All right. So this, let's create a partition. Okay, let's create a mesh. It's not wanting to mesh. Let me see something. Let's go smaller. So let's go to 0.2. And let's mesh. All right. Yes. It doesn't matter. Like for rigid bodies, Abaqus knows that it's rigid, so the meshing there doesn't really matter. Okay, so still we failed. Let's try to get this done. So let's do incremental meshing. So we are gonna mesh by parts. So this is mesh region. So let's first mesh the spring. Okay, it meshed. Let's mesh this. It meshed. Let's mesh this. It meshed. Let's mesh this. It meshed. And let's mesh this. It meshed. How do I figure this out? Believe me, it's only experience. Like, right, there's a Abaqus course coming soon. Explicit meshing analysis. Sorry, meshing for explicit analysis. So it's complicated, right? For at least for 3D. For 2D, you're never gonna see this. Like, it's really hard to be complicated in terms of 2D modeling. Now, that being said, if you have problems meshing, send me your files, and we can do it over Zoom, or I can help you how I did it. So that's how I've been working with some of the groups here. All right.
Do you have any version of Abaqus? Because there's like
I have the latest, so I can open anything.
Oh, really?
Yeah. All right. So meshed. Let's quickly create a job. So create a job. So Spring compression, and let's write an input. All right. And I'm gonna have to run this from the Abaqus command, right? Sorry, from the command prompt. So I'm gonna go to this folder, right? And this is how you run Abaqus in parallel. You can also do it from here. Like if you go here, so like edit parallelization, and then you can say here that run with 16 CPUs. All right, and then you right click here and submit. This computer, it doesn't allow me to do that. I don't know why. So the way that I run from the command line is Abaqus job Spring compression, right? That's so Spring compression, CPUs 16, int is just that show me everything on the screen. And if I have a job with the same name, don't ask me to delete it or not. Like just go ahead and rewrite everything. So let's kill the computer. I hope it runs. You never know. I did this right before coming to class, and I didn't have problems with the machine.
That's all. Just makes some crazy software. Yeah.
All right. In the meantime, let me show you something. If we don't get to finish the second example here in YouTube, my channel. Now you guys saw that I like Formula One. I have one tutorial here that is called Impact, right? So it's a projectile that is penetrating a plate. That's what we are gonna do today. So you can call it a bullet, you can call it anything you like. For my work, it's not a bullet, believe it or not, but we have projectiles traveling at the speed of sound, and they impact plates. And do you know what happens when they impact two aluminum plates? They weld the aluminum plates.
Do you work at Sweary?
No, I work at Pacific National Labs.
Okay.
All right, let's see how the simulation is going. It didn't run. Let's try with less CPUs.
Yeah. Can we watch that sunset you have?
Sorry?
You have a sunset video. Can we watch that?
A what?
A sunset video on your YouTube channel. Says we'll bring flashing minutes.
Let's see if I have something wrong in mesh. Everything looks fine. Let's try one more time. If not, I'm gonna show the results. Oh, okay. No, right. So I think that the speed that we are applying is too high, all right? Because it says excessive deformation. So let's reduce it a little bit. So just so you guys trust me that this runs, all right? But then we can go to the cool results that I have created already. So let's write input. I don't want to see this warning again. And let's run it again. Okay. Okay, it's running. All right, so after you run this, let's hope this doesn't crash. All right, it's running. So after we complete this, I'm gonna open the spring. Sorry, I don't want to open that one. Let's open this one that already completed. So let's take a look from the front. And let's go to the deform configuration. So do you guys think that this is stressed or not? It should be, right? So there's something wrong with what? With my scale. No, this is the final step. So here in the step, it's already at the end. So I go here to contour options, and then in my limits, I'm gonna say, hey, the highest stress that you can give me is gonna be, I don't know, 500 megapascals. Now look at how this changes. Now it is stressed. All right? And you, here, the deformation, I'm gonna go here, and the deformation scale factor is 1. If I go crazy, sometimes the deformations are really small, so what Abaqus does is, hey, your deformations are amplified by 1,000, and then you get something like this. And that happens a lot of the times, right? So you have to be cautious on what the scale factor that Abaqus is using. So let's see how this is working. So in the beginning, nothing. And as we start increasing, compressing, then it's going up, then it's going down, then it's going up, then it's going down, then it's going up. So it's just bouncing. I can, hey, Abaqus, show me how the displacement of this node looks like, right? Because that's how you do what in physics, mass spring system or spring and pendulum system, whatever you guys want, you can do it in here. So I'm gonna go here to results, history output, and hey, I want to see the vertical displacement of that node plotted. So this is how it looks. It damps, but the speed that we applied is so huge for a 10 millimeter spring. 10 millimeter spring is something like this. So it's like, I'm like really hard, and I don't have friction, right? So if I were to really damp this, I will have to add damping to my system. So what do you think about this example? You guys like it? Let's see if my model run. Oh, it completed successfully. So those who didn't trust me. So that spring is this one. Let's see how it looks. So it's this. The speed is too low, right? So I added a spring velocity of 10, right? So let's see from this angle in here. But it's compressing, and then you see the wave traveling and then going back again up, right? Everyone saw that? So going down, the wave is traveling down, and then it goes back up, and then, yeah, this is really nice. Questions? This is gonna be recorded, right? So if you want to do this at home, some of you have springs. Montana is not here, but she has springs. Who else is doing? You are doing springs. So this is how we can do it as well. Your the damper, the damper that you added doesn't compress. If we add torsion to this, it will compress as well. Yeah. All right. Now let's go to the projectile impact. All right. I think we have enough time. All right. So I'm gonna create a new model. So it's gonna be called projectile impact. I'm gonna upload these files as well. So part number 1. Quickly, I'm gonna create a plate. All right, using a revolution technique. And the plate, I have the dimensions in here. So the radius is 5 millimeters. And the height is 0.2 millimeters. So I'm gonna create a rectangle that starts in 0, 0, and then it ends in 5, 0.2. So that's gonna be my plate, or at least half of it. I'm gonna revolve it. I'm gonna revolve it 360 degrees. All right. Where is the bullet gonna impact our plate? In the center. So I want really refined mesh in the center, and in the outside of the plate, I don't want anything. I want as coarse elements as possible, right? So I'm gonna create a partition here, and I'm gonna just quickly create a circle like this. All right. And if we look below the plate, we haven't like partition everything. So I have to extrude that drawing, and it's called sweep. So I'm gonna go here on this menu, and then I'm gonna say sweep edges. Which edge do I want to sweep? This one. Which direction? This is the direction of sweeping, right? So it's showing me an arrow. So this circular edge that I just selected, I'm just gonna like cut it throughout the whole plate. And now the partition is complete. No, sorry, I forgot to say yes. So this one, extrude along direction, okay, create partition, and now in the bottom we have everything, right? Okay, now, quick plasticity damage theory here. How were we adding plasticity in our model? Using a table, right? Anyone wonders how we get the values out of that table? Some people is called, for example, this guy, the two guys, one is called Johnson and the other one is called Cook. They created a material model that is called Johnson-Cook material model, right? So what they're basically doing is that, hey, let's try this material, let's get all the mechanical properties, and instead of having like tabular values, let's fit a curve, right? So we have a curve now that is gonna define our plastic behavior, right? How to search for that? I literally just went and searched for aluminum Johnson-Cook properties. This is really advanced. I'm not asking you guys to do this, but this is how I do it. Then I want elements to be deleted, right? So I want damage in the elements, right? So whenever a bullet is impacting a plate at a really high speed, that plate is gonna fly everywhere. And in order to do that, those guys, Johnson and Cook, they also created something that is called damage modeling, right? So if you add these values in there, you're gonna allow Abaqus to delete the elements of your simulation, all right? That you can use it for fracture, for crack propagation, like, hey, let's pull this plate, but whenever these elements in here have reached a certain amount of plasticity, just delete them from my model. I don't need them anymore. So that's called damage modeling, all right? So I'm gonna go here to Abaqus, and I'm gonna create that material. So aluminum 661, density, we already know what the density is, 2.7 e to the 9. Mechanical. Elastic is going to behave the same. So Young's modulus of 68 gigapascals and Poisson's ratio of 0.3. Then the plasticity. Instead of having a table, I'm going to go here to Johnson-Cook. And I'm just simply going to go in there and add those properties. So let me do that. This one. So A, 324, B, 114, N, 0.42, M, 1.34, melting temperature, 650, transition temperature, 25 degrees. All right? We don't care about this. They did all the work for us already. I'm gonna add this sub option of a strain rate dependent. So I'm just gonna go here to Johnson-Cook and I'm gonna add the C property, which is 0.002 and 1. All right. And I'm gonna add damage. And also Johnson-Cook. D1, 0. Let's zoom a little bit. Negative 0.77, 1.45, negative 0.47, 0, 1.6, melting temperature 650, transition temperature 20, and reference and strain rate is 1. And in here in the sub options, I'm gonna say that whenever that element has an energy of 0.01, just delete it. Don't worry about that. It's just simply that once that material is damaged, I want it out of the model, right? Okay, I already created the material. Quickly, I'm gonna create this section. I'm gonna assign it to everything in here. Okay, and before I forget, I'm gonna create a set here in the outside. So outside of plate. And it's gonna be these edges in here. Sorry, this here in the outside. Okay. Am I missing the bullet or not? Yes, I forgot about the bullet. So I'm gonna model the projectile. It's gonna be what? Discrete rigid. All right. And we can use a shell. And using a revolution technique. Just simply is gonna be a hollow piece that is gonna be rigid. That bullet is not gonna feel anything. It's just gonna go through everything. All right. Okay. So let's model that. So it's gonna be 0.0, then here 0.5, and then here like that. It doesn't really matter a lot. I'm just gonna round it in here to make it smoother, and I'm gonna revolve it 360 like that. Okay, that's gonna be my projectile. I'm gonna add a reference point in here. All right. Why do I have to add a reference point? Because that bullet is also gonna be rigid. So I have to also add a constraint and say, hey, all the nodes that belong to this shell bullet in here are gonna be referenced to the reference point. Okay. Let's quickly add an assembly. And let's add everything. Okay. Let's bring the bullet up a little bit. So I'm gonna go here to translate. I'm gonna translate this instance, and I'm gonna translate it in Y 0,1 C,0. All right. So it's a little bit. I just moved it upwards a little bit. Okay. Let's create the boundary conditions first. So, sorry, no, let's create a constraint. So again, rigid body constraint, the body or the elements that are gonna be restricted are these that belong to the bullet, right? And the reference point is gonna be this one. Now everything is gonna be moving with respect to the reference point. Let's add the boundary conditions. So this plate, my edge, the one that I created before, that outside of the plate, someone is gonna be holding that plate. So I'm just gonna say all the nodes in the outside of that plate are gonna be fixed. That way, once the bullet impacts the plate doesn't go flying. The bullet is only allowed to move in which direction? Vertical Y, right? So I'm gonna say, hey, I'm gonna add a new boundary condition to this reference point, and I'm only gonna allow that point to move vertically. How did I add the velocity in the spring system? A predefined field, right? Something that is called predefined fields. So I'm gonna go here to predefine field. I'm gonna add an initial velocity, and this plate, so I already created a set for that reference point, is gonna be traveling at 150 meters per second. That's half the speed of sound. All right, so negative 150 meters per second, but I'm working in millimeters. So 1, 2, 3 more zeros. Okay, always be conscious about that. Let's go here because I had some help in here. So velocity, radius, h. So we have to add a mass to the bullet. How do we do that? We go here to part. I'm gonna go here to properties, special, inertia, and I'm gonna create a point mass inertia. And I'm gonna do it for this reference point. And I'm gonna say that that point or the bullet system is gonna weigh 100 grams. And 100 grams is equal to this in tons. Okay? I'm just adding mass to that point. Otherwise, it's not gonna penetrate the plate because it's a massless system. Does the plate already has mass or not? We added a mass to the plate or not? We did, right? Because we said that plate has a material and we gave the density of the material, right? So that's the reason why we are adding mass to that reference point. Okay, let's quickly go here to the step, and it's gonna go a explicit step. The time I have here 3e⁻⁵ seconds. So 3e⁻⁵ seconds. Because this is super quick, we don't need any mass scaling. So this is gonna work just fine. And let's quickly go to mesh. All right. So I'm gonna mesh this. I'm just gonna mesh it as is. I don't care. 0.1. I'm gonna mesh it. The element type, super important. It has to be explicit. And let's mesh the plate. So for the whole plate, a seed of 0.7, so 0.5 is fine. But then I'm gonna say, hey, for this region in here, I want a finer mesh of 0.1. And let's see what type of mesh Abaqus gives me. That one is good enough. It's refining the middle where we are gonna impact, and it's coarse in the outside where we don't need any information. Oh, you're the one doing springs as well. Okay. Here, remember to set it as explicit. Sorry, here in S4R. Let's set it as explicit. All right. What are we missing? Please help me.
Contact.
Contact. All right. So for contact, we have to go 2 steps. Actually, let's go here. Interactions. Abaqus is, if not, I'm sure Abaqus is the best doing contact. It's by far the only reason we use Abaqus. The general contact algorithm they have is the best in the world. Like, you just add contact and that thing works. I don't know how. I have seen several dissertations, doctoral dissertations, on just how to do contact. And they are super easy, like 2 elements, and how they penetrate and the different possibilities. What happens if this element is like this, like that? It's a super complicated algorithm. Abaqus is by far the best doing contact. So I'm just gonna add a general contact. So Abaqus is gonna take care of it. I just have to give some properties to the contact. So here, I'm gonna create some interaction properties. I'm gonna say that we are gonna have normal contact, so normal behavior. So I'm gonna allow my surfaces to interact in a normal way. And I'm also gonna have tangential behavior, and it's gonna be with a friction coefficient of 0.3. So that's simply if you have shear, or at some point you see shear. Here we don't see shear, but what happens once the bullet penetrates the plate? It's shearing the plate. So we need this definition as well. And that's it. We just define contact. I'm gonna go back to the mesh because I forgot something. Here in the plate, I'm gonna go here to this menu and I'm gonna say, hey, help me with the distortion control. I don't want highly distorted elements. And I want my elements to be deleted. All right. Once the element has reached the damage criterion, remove it from my model. Okay. That's pretty much it. I think we're ready to go. Here in the field output, I'm gonna add this status variable. That way, the elements that are deleted, we don't see them. Otherwise, we just see a huge mess. All right. So let's see if this runs. So I'm gonna create a job that is gonna be called Proj impact. Impact. All right. I input, and I'm gonna go to my Abaqus prompt, and I'm just gonna change the job name. So it's gonna be called Projectile Impact, and with 12 CPUs. Let's see if this runs. It should. Completed. Let's see if we got garbage or not. I'm gonna go here to my results, and I'm gonna open the one that we just created, Proj Impact. All right, let's see the surprise in here. Wow. So the bullet went through, and look at the hole it left in our plate. We can go here to the frame selector, and here is how it impacts. If we look at the bottom, from the bottom, it's really nice, isn't it? So let's do a little bit of analysis. Let's look at the plastic strain.
Is there a way to export that little video?
Yes, I'm gonna do it in a second. So here, look at the plastic strain. Sorry, I have my limits off. So we don't see it here because we didn't ask for many frames, but those elements were red, like really, really, really high plastic strain. Those are doing nothing to the model. Like if you have something really high amount of plastic deformation, it behaves like a rubber. Like you apply a little bit of load and it moves everywhere. So instead of adding noise to our system, once we reach a failure criterion, hey, let's remove it from our model because actually it's doing nothing, right? And then we can allow the bullet to penetrate. So now you can put ballistic impacts in your resume. Yeah, but this is the right way to do it. And of course, like with better mesh, being more thorough in terms of the mechanical properties. Once you hit something with really high speed, you have something that we call a strain rate hardening effects. And is that when you pull something super quick, it's actually more difficult to deform.
So it suddenly becomes brittle.
Not brittle, it becomes harder with a high speed. So pulling a material at 5 meters per second, the material, if you put it at 200 meters per second, is completely different. One example, what happens if you're under the pool and you're doing like this? You can move the hand freely. Try to do this. You can't, right? So it's a concept that is similar to the Stokes number, right? Right? No, yes, Stokes, no. How do you call, yeah, like the drag system. So it's more or less like that. The higher the speed, the higher the drag that you're going to have in your system. For these mechanical properties, it's also the same. In some cases, you have materials that are really strain rate dependent, and if you pull them super quick, they completely behave differently. All right. I hope you guys enjoyed it. This is really advanced stuff. We're gonna do fracture next, right? So how we propagate a crack. We created a hole in here, but then it's like how we can propagate a crack and those type of things, right?
I have a the tensor.
Hey.
Well, we're in the